Hello everyone. In today's discussion, I shall discuss about the macroscopic microscopic view of the diffusion equation, and in terms of fluxes and Fick's laws. So let us start our discussion. So in the last lecture or in the last tutorial, we learned how to derive the diffusion equation directly from the problem of random walk. In today's discussion, we shall try to understand the diffusion equation which we have derived in terms of fluxes, how to derive that from the fluxes. So let us start. So let us consider a three-dimensional box okay. So this is x, y, and this is z direction. So consider this plane, okay. So let's say this is the x-axis and this is the point x, this is point x plus L. Let us consider that the number of particles at this plane, which is this plane. So let's say this is x, this coordinate is, so let us consider that we are on x-axis, so other coordinates are fixed and only x is changing. So if the number of particles at point x is nx, and let's say at point x plus L it is nx plus L, is function of x plus L, and they are not equal, so there is some inhomogeneity in the particle number. Now we want to know that what is the flux of particle in x direction. So what is flux? Flux is usually defined as, for our case, is the particle which are for whose flux we want to know. So this is the number of particle crossing a cross-sectional area, so per unit area per unit time. So number of particles crossing per unit area per unit time is the flux, okay, through a surface. So number of particles crossing per unit area per unit time, okay. So let's say so for now just consider that this L is the our mean free path. You can consider actually any distance, so let's say L is a distance, and so let's say so we have assumed that at time t, at position x, the number of particles are nx, and at position x plus L, number of particles are nx plus L. So after okay, so for our convenience or for you to understand well, let's say L is the mean free path, okay, to have a connection from the previous discussion. So let's say L is the mean free path. So after time t plus tau, where tau is again the mean collisional time, then half of the particle at x will move from left to right. So half of the particle will move. What is the probability that half of the particle will move from left to right? And similarly, at x plus l, half of the particle will move from right to left. Okay. So the net number of particles crossing this dashed line is equals to, so net number of particles crossing dashed line is equal to, or let's say particle crossing right is equal to 1 by 2 nx minus nx plus l. Okay, or we can write it as more nx plus l minus nx. Now what is flux? So flux will be, let us denote it with j. So the flux in x direction will be jx is equals to, so number of particle crossing per unit area per unit time. So this is the total number of particle crossing from in the x direction. So number of particles divided by area and tau, per unit area per unit time. Okay, so tau is the mean collisional time for our case. Now let us divide and multiply by L. So what will we get? 1 by 2 L by tau and nx plus L AL minus nx by AL. So what is this number? This is the number density. Above is the numerator has the total number of particles, and this is the volume of the small element around that point. So this is the number density. So you are familiar with the number density nx plus L. So nx and nx plus L. Okay. So minus 1 by 2 L by tau nx plus L minus nx. Okay. Now divide by again by L, then what will you have? Minus 1 by 2 L square by tau, and this is what? Nx plus L minus nx over L. This is the, so we can write it as minus 1 over 2 L square by tau del nx over del x, right? Jx. And what is this quantity? This is the familiar quantity, right? You have seen this earlier. We have defined d is equals to 1 by 2 LV, right? See your notes. Then this is L square by 2 tau. Okay, this is the diffusion coefficient. So what is this? Jx is minus d del n over del x. Okay. Similarly, there will be currents in x direction, in y direction and z direction. Jy will be minus d del ny. So okay, let us not write it as a function of x, because it will be a function of x, y, z, all the quantities. Del y and jz will be minus d del n over del z. Okay, in general one can write the current density and flux are actually similar things. So current density is the particle currents, number of particles crossing per unit area per unit time. So that is current density and flux. Okay, so J minus D gradient of N. So this is the Fick's law. Or Fick's first law. So the current will appear when there is a gradient in the number density. If the particles are uniformly distributed, then of course there is no flux. And so the situation is that in the case of dye also, there is a non-equilibrium distribution, right? Some particles are gathered at one place very densely, and other place there are no particles of dye particles. So it will start spreading out, and when there is a uniform mixture. So that will be the equilibrium situation. This is also the equilibrium situation because the average quantities are not changing with time, but uniformly at time infinity they will mix. The situation will be a uniform mixture. So the diffusion will take place up to that point when gradient of n is 0. Okay. So there can be many situations. Let's say the current can be constant. When there is a constant gradient applied, current can be 0, and many cases. So let us first note one thing, because sometimes we have to have a clear idea of the dimensions or units. Okay, just to put these units in your mind. So n, if n is measured like particles per centimeter cube, then J will be, so J is the current or the flux. J has units then particles per centimeter cube, centimeter square. And if n is in moles, then this J will have a unit in moles per centimeter square. Okay. So this is the Fick's first law. Now let us look into that Fick's second law, and that has a similar form to the diffusion equation which we have derived earlier. So Fick's second law. So it is derived actually from the first law, provided that the total number of particles are conserved. Okay, that is, the particles, this is inside the box, the total number of particles are conserved. Particles are neither created or they are not lost by any means. So the number of particles, so the change in the number of particles inside this box is only due to the currents or the fluxes through the surfaces. Okay. So let me write it. So this is only applicable, this formula which I am going to derive is only applicable when total number of particles are conserved. Okay. So again, let us consider only to have just to quick view. Let's say this is our point X, this is X plus L, and the current density at this surface is Jx. J is function of time, and at this point Jx plus L and T. Okay, and this has an area A. So in this case also the surfaces have the area A. Okay, so in time period tau, let's say in time tau, so then Jx, a tau number of particles will enter from the left. Okay, because this is the number of particle per unit area per unit time. So if you multiply with area and time, you will get the total number of particle moving from X or entering from this surface. From right to left. And similarly, so this is the, okay, let me write it clearly once. Number of particles entering from right to left is jx a tau, jx at x, and from left to right it is jx x plus l a tau. Okay, and the volume of the box is then, so the volume of the box, oops, yeah, volume of the box is a tau, and so the number of particles, a change in the number of particles is what? Change in the number of particles in time tau will be 1 over tau, number density, sorry, nx plus tau minus nx. This is the number density change in the time period tau, and this is accompanied by what? Minus 1 by tau jx plus l minus jx a, okay, tau. Okay, first let me write it in this way. So what is nx? What is this change? This is jx plus l minus jx into a tau. So the total number of particle enters in time t is this, and if you divide by the volume, then this will give me the total number of the net change in the number density. Okay, because I divided by the volume. Now the rate of change of this number density, let's say divided by tau, 1 over tau. So there will be a minus sign because we are considering the net change in the right direction. So what is this quantity? Left hand side, this is del n over del t. This is tau will cancel out, a will also cancel out, minus l jx plus l minus jx. Okay, so what we have now, del n over del t is equals to minus del jx over del x. Yeah, so this is for in x directions, so this is nx. Similarly, we will have other three components, and combining those three, we will have del n over del t plus del dot j is equals to 0. This is also known as continuity equation. Okay, continuity equation. If you substitute back the value of j from previous, the Fick's first law, then you will have the similar form of diffusion equation, del n by del t and minus d del j by del x, and j is what? Minus d, sorry, minus d is coming from j, minus d del n x over del x. Another three components, del by del y, del ny by del y plus del by del z, del nz over del z. So this is the in minus t Laplace square, and this operator del x2 del y2 plus del z2 is the Laplacian. Okay, so Laplacian n del n over del t. So this is Fick's second law, diffusion equation. Fick's second law. Or diffusion equation. So for our case, when there is only diffusion is happening due to the thermal fluctuations. Let's say because there are molecular vibrations or molecular energies coming due to the thermal energy. So if your particles are in room temperature, their velocities will be, the kinetic energy is actually some factor times kT. Okay, so the thermal energy is actually converted to their motion, and this motion is random, and so the current is coming from that is proportional to gradient of n. But in many cases there can be situation due to some external forcing or pressure gradient or some other means, there can be situations where other currents can also be present. Then this equation, continuity equation, will have other terms also, but this is the most general form. Del n by del t plus del dot j is equals to 0. J can have many, j can be from many sources, but this particular equation is when j is coming only due to the gradient in the particle density, and that is the Fick's second law. Okay. One more case is very familiar to this diffusion equation, which is the case of thermal conduction. So when you heat up the fluid, let's say you turn on your stove, let's say this is the water, and you turn on your stove, flame is low, then what is happening? Then lower particles at the bottom, they get excited, they vibrate quickly, then they impart this collision to other particles, and this process is the diffusion. The heat or the temperature equation then satisfy this Fick's law. In place of n, then we will have del t over t is equals to minus alpha del square t, where alpha is the thermal diffusivity, coefficient of thermal diffusivity. So the thermal energy is diffusing. Okay, earlier case the particle number is diffusing, but in our case this is temperature is diffusing. Okay, or heat energy you can say. So this is the diffusion of temperature rather than the diffusion of particle number, and this is called the Fourier's law. And for here, in the case when we have discussed the number of this Fick's law for diffusion of the number of particles, we have considered that the total number of particles are constant. When we have this situation where temperature is diffusing, then this is the conservation of energy. So total energy is conserved. Energy is conserved. Okay. Heat flow proportional to temperature difference. This is also known as Fourier's law. Actually, this is not Fourier's law. The law that thermal current is proportional to minus some kappa times, or let's say minus alpha times gradient of t. This is the Fourier's law. So this is the analog of Fick's law in the case of particles. Okay, so this law says that the rate of heat flow is proportional to the temperature difference. Okay, GQ you can say, rate of heat flow. Now we shall discuss very briefly about one more phenomena which is not the equilibrium case. It is the case of convection. Very briefly, just to have an idea that there can be more ways to change in due to so that the number of particles or temperature etc. can change, and that is not only due to diffusion, but if there are external current present, there are external forcing present, then there can be a phenomena called convection. So in earlier situation we have considered the system in thermal equilibrium. The motion of molecules are due to random collisions and particle velocity is due to the thermal energy. Okay, but if there are external source, let's say there are convection currents. Let's say you are stirring your coffee. So if you have put it, let's say this is your coffee and you have some sugar. If you will not stir it, the sugar will diffuse only due to the conduction. And we have seen in case when we have discussed the diffusion that this time is actually very long. So if you just put your sugar and if you wait that your sugar will mix, your coffee will be cold by that time. It's a very long time. So you stir it, yeah, right? So means you are injecting some external force in this medium, and the stirring causes some extra currents that are not equilibrium case, that are non-equilibrium case. Let's say you have gravity present, so there can be density stratification, buoyancy force, etc. So these are the cases when there are convection current, convection rolls. Maybe you have seen some kind of rolls. So when you heat up this very let's say the temperature is very high or the heat flow, you turn on the lamp fully, then this fluid will start making all kind of other motions, which is not due to diffusion, but there are currents present, thermal currents. In that case, the J will be proportional to the NV. V is the coming due to the convection. Okay, this case will add up, then your continuity equation will be modified. Divergence of NV minus gradient of N. Okay, this is 0. Del N over del T plus, actually above is, I don't know, yeah, that is continuity equation we can say. So divergence of NV is equals to, okay, there is D gradient of N when there is a convection present. So this equation is known as convection diffusion equation. So this J can be from any different mechanisms also. So J will add up if there are other mechanism present. So this equation will modify by just the additional term due to J. So in the presence of convection, which is usually present in our system, it is very difficult to observe diffusion. For diffusion, the best place is the biology. Okay, because in biological system, temperature is almost constant, convection currents are almost non-zero, and you can actually observe this in biology. And in the continuation, we will actually now discuss another important phenomena of Brownian motion related. So the first observation of Brownian motion was actually due to a botanist. He did some experiment in his lab, and people discovered that thing as a Brownian motion later. So we will discuss next this topic. Thank you very much.